If you think science is just a stuffy old book full of facts, I want you to think again. Today, we're going to dive into what science really is, a thrilling, non-stop adventure that's unfolding all around us, right now.
Take a look at this. This really captures the whole spirit of our journey, doesn't it? Something as simple as flying a paper plane has actually sparked real scientific curiosity about flight for centuries. From the very first inventors to today's engineers, that dream of soaring through the skies, it often started with this exact kind of simple, playful curiosity.
So, here's the most important thing to remember. Science isn't some final destination with all the answers neatly filed away. Nope. It's more like an open invitation. An invitation to ask questions, to get your hands dirty, and to try and make sense of this beautiful, complicated world we live in. It's something you do, not just something you read about.
Now, every great explorer needs the right tools, right? And when you're a scientific adventurer, you don't need $1 million lab. The most essential gear, well, it's something we all already have. Here are the 3 essentials. First up, question. Everything. You've got to feed that sense of wonder about why things are the way they are. Second, experiment. Don't just wonder, test your ideas. And third, explore. You have to get out there and see the world for yourself. This is where real discovery happens.
And this right here just drives the point home. Look, classrooms are obviously important, but true understanding, that often comes from real-world, hands-on experience. Science is happening all the time. In your kitchen, in your backyard, literally everywhere.
Okay, so we've got our toolkit ready. Let's pull out our adventure map for a second. This will give you a taste of the incredible places we can go just by asking some simple questions about the world right in front of us.
Let's start with something basic. Taste. Why does a lemon make you pucker up, while a mango is so sweet? Well, the answer is all about their chemical makeup. Citric acid versus natural sugars. See? A simple question about lunch can lead you right into the world of chemistry.
Or think about this. We flip a switch, and boom, a whole room lights up. But what's actually making that happen? The answer takes you into conductivity and resistance, these core ideas in physics that explain how electricity zips through a tiny wire and makes it glow.
We see change everywhere. Ice melts into water. Batteries run out of juice. But here's the big question. Can you turn back the clock? This leads us to the huge difference between physical changes, like refreezing water, and chemical changes, like a dead battery, which, well, that's a whole lot harder to undo.
How about something we take for granted, like time? Long before we had clocks on our phones, people just looked up. They used the sun's path across the sky and the shadows it cast to measure the day. It's an amazing link between ancient astronomy and our modern understanding of light.
And let's take that idea of shadows and scale it up, way up. It's not just a stick in the ground that can cast a shadow. The Earth and the Moon do it to each other, creating these incredible events we call eclipses. All of a sudden, a simple question about a shadow has us talking about how the solar system works.
You see, all these questions eventually lead us somewhere deeper. It stops being just about how the world works and starts being about finding our own place within it. And this is where science meets responsibility.
This really hits the nail on the head. Being a scientific explorer today means understanding how we connect to the world around us. It's about using what we learn to tackle huge environmental challenges and hopefully help build a more sustainable future for everyone.
And that's possible because none of this stuff exists in a vacuum. It's all connected. The physics of light helps us understand the biology of a leaf. The chemistry inside a battery depends on geology. It's all woven together into this rich, incredible tapestry of knowledge.
Which brings us to our final, and maybe the most important, stop on our journey today. It's about developing a true explorer's mindset. And here's the secret. It's not about having all the answers. The real power lies in asking really, really good questions.
Think about it. We're all trained to find the right answer to a question. But the people who make the biggest breakthroughs, they do the exact opposite. They look at an answer, an observation, a weird result, and they ask a brilliant, creative, new question about it. So let's try it.
Okay, here's an answer for you. Your challenge is to work backward. Think like a scientist. What kind of curious or funny or totally unexpected question could possibly lead to this as the answer?
All right, one more, a famous one. The answer is 42. Now, there are infinite possibilities here. What question could you dream up where the only possible response is simply 42?
And that's really the heart of it all.
The whole journey of science is fueled by our ability to wonder, because sometimes the most powerful thing in the universe isn't finding the answer, it's daring to ask a better question. Now get out there and keep exploring.
Today, we're diving into a really cool chemical mystery. We're going to uncover the hidden nature of stuff all around us. Finding out if they're acidic, basic, or even neutral. So let's get right into it.
Okay, picture this. You're at some cool science event, right? And someone hands you what looks like a totally blank piece of paper. Then, they spritz it with some clear liquid and bam! A message just appears out of thin air, saying, "Welcome to the wonderful world of science." I mean, that feels like straight-up magic, doesn't it?
So, what's the deal with this invisible ink? Is it a magic trick? Some kind of sleight of hand? Or is there something more scientific going on? Well, that's exactly what we're here to figure out. And, spoiler alert, it all boils down to some really awesome chemistry.
So first up, let's pull back the curtain on that mysterious message. We're going to break down exactly how it's possible.
And the secret? Well, it turns out it's not magic at all. It's all about how different substances react with each other and, in the process, create these amazing color changes. And that reaction is the key to solving this whole mystery.
This leads us right to the heart of how this chemical magic actually works. We need to learn how to speak the secret language of color.
The tools that let us read this language? They're called acid-base indicators. You can think of them like chemical decoders. They're these special substances that literally change color when they come into contact with an acid or a base. It's how they reveal a solution's secret identity.
And what's so cool is that these chemical detectives aren't just found in a lab. They're literally all around us in nature. The most famous one, litmus, actually comes from lichen. But you can find these indicators in everyday things, like red roses, hibiscus flowers, purple cabbage, even the turmeric you have in your kitchen spice rack.
Okay, so what are these indicators actually showing us? Well, they help us sort pretty much any substance into one of three simple categories. Is it an acid, a base, or is it neutral?
All right, let's talk about the litmus tests. This is the golden rule, and it's super simple. Acids, they turn blue litmus paper red. And on the other hand, bases turn red litmus paper blue. Just remember this: acid red, base blue. Easy, right?
But wait, what happens if you test something and nothing happens? If it doesn't change the color of the blue paper or the red paper, well, that's actually a result too. It tells you the substance is neutral. It's not an acid and it's not a base.
Okay, we've got the rules. Now for the really fun part. Let's put this knowledge to work and become chemical detectives ourselves by testing some stuff you can find right in your own home.
You can grab all sorts of things, like lemon juice, a bit of soap mixed with water, some vinegar, even just plain old tap water. Every single one of them has a hidden chemical nature, and now we know how to uncover it.
So if we take some vinegar or lemon juice and dip a piece of blue litmus paper in, we'll see it turn red almost instantly. And according to our rule, that means, yep, they're acidic.
Now let's try the opposite. What if we test something like a soap solution or maybe some baking soda? This time we use the red litmus paper, and it turns blue. That's the telltale sign that these are basic.
Okay, you've seen how it works. I think you're ready for a final challenge. Let's see if you can put your new detective skills to the test and decode a few unknown solutions.
So here's the mystery. We've got three unknown solutions. Let's call them A, B, and C. We've tested them, and we have three clues, one for each. Your mission is to figure out what they are based on these reactions.
Let's break it down. Solution A. The clue says it turned red litmus blue. Okay, what does that tell us? Remember the rule? Red to blue means it's basic. Perfect. One down. Okay, let's skip to solution C. It turned the red rose extract green. Now this is where it gets interesting, because different indicators have different color codes, and the rule for red rose extract is that turning green means it's a basic solution. So solution C is also a base. Pretty cool, huh?
See, you really don't need some high-tech lab to start exploring chemistry. With just a couple of simple rules and some of those natural indicators we talked about, your kitchen basically becomes your own personal laboratory.
All right, let's do a super quick recap of the main takeaways. First, substances are either acidic, basic, or neutral. Second, we figure this out using acid-base indicators, which are just things that change color. Third, the big rule to remember. Acids turn blue litmus red, and bases turn red litmus blue. And finally, don't forget that nature has given us a ton of these indicators already.
Once you start thinking this way, you'll realize the world is just full of these little chemical secrets. The colors are the clues, and now you know how to read them.
So I'll leave you with this question. Now that you know the rules, now that you can decode this language of color, what kind of colorful secrets are hiding in your own home, right under your nose? Go find out. You might be surprised by what you discover.
You know, what if I told you that the secret to this massive network of power that runs our entire world isn't hidden away in some giant power plant? What if I told you it could be sitting in a drawer right in your own kitchen? Well, today we're going to unlock that secret together. Just think about it for a second. From the moment you woke up to right now, how many things have you used that need electricity? The list is probably way, way longer than you think. I mean, your morning coffee, that toaster, the microwave you used for lunch, all of it, zap, brought to life by electricity. And how'd you get around? Whether it was a train, your car, or even just an escalator at the mall, you were moving thanks to electrical power. Oh, and that device you're probably holding in your hand or watching this on right now, your phone, it's this little portal to the entire world. And guess what? It's all powered by the exact same basic ideas we're about to get into. Electricity literally pushes back the darkness, lighting up our homes, our streets, our whole world. But to really get a handle on this incredible power, we need to go back to basics. We need to look at how one simple light is made. Right. To understand the really big picture, we're going to start small. Forget about the massive power grid for a minute. We're going to deconstruct a simple torchlight to find the fundamental principles of all electricity. Yep, this humble little device. It holds the key to understanding how pretty much all electrical devices work. Seriously, if we can figure out the torchlight, we can grasp the core ideas of electricity. So, what's inside? Okay, so at the very heart of the torch is the electric cell. This is its portable power source. Every single cell has two connection points, what we call terminals. There's a positive end, that's the little metal cap, and a negative end, which is the flat metal disc on the bottom. And, if you see more than one of those cells inside something, which you often do in a torchlight, well then technically you've got yourself a battery. You just combine the cells, connecting the positive of one to the negative of the next to get a bit more juice. So we have our power source. Great. Now, how do we get that power from the cell all the way to that little lamp to make it glow? We need to build a path for it. We need to make a simple circuit. Let's break it down into 4 essential parts. It's kind of like a recipe. First, you need the power source. That's our electric cell. Second, you need a path for the electricity to travel on. That's usually going to be some wires. Third, you need a load. That's the thing you actually want to power, like our lamp. And finally, you need control, a switch to turn it on and off. Okay, look at this. For that lamp to light up, there has to be a complete, unbroken loop. This flow of electricity is what we call the current. See how it travels out of the positive terminal, goes through the wire and the switch, powers up the lamp, and then travels all the way back to the negative terminal. It's a complete circle of power. So that brings us to the switch. Its role is absolutely crucial. You can think of the switch as the gatekeeper. It's a really simple device that acts like a drawbridge on our electrical path. It can either connect the path or create a gap. When you flip that switch to on, you're lowering the drawbridge. The circuit becomes closed, which means the path is complete and the current can flow. But when you flip it to off, you're raising the bridge. The circuit is now open. There's a gap the electricity can't cross and the lamp goes dark. Simple as that. Okay, we've talked about the path, but what is that path actually made of? And why are some materials used for the path itself, while other materials are used to, keep us safe from it? This brings us to conductors and insulators. This is such a great question because the answer reveals another really fundamental concept. Why do we use metal for the inside of a wire but cover it with plastic on the outside? Well, it's all because different materials behave very differently when electricity tries to pass through them. So some materials, which we call conductors, they let electric current flow through them super easily. Think of metals like copper, or even the keys and coins in your pocket. But other materials, called insulators, do the exact opposite. They block the flow of electricity. Things like rubber, plastic, and wood are all fantastic insulators. And here's the thing. You need both to make a safe, working electrical device. You use conductors, like copper, to create the path so the electricity can go where you want it to. And then you use insulators, like plastic, to wrap around those conductors to keep the electricity contained and, more importantly, to protect you from getting an electric shock. And that right there brings us to probably the most important part of this whole explainer. Look, understanding these basic principles isn't just a fun little science experiment, it is absolutely critical for your safety. I'm sure you've seen this sign before. It's a universal warning for a reason. Electricity can be incredibly dangerous if it's not handled with care and respect. This is not something to play around with outside of a controlled setting with, low power cells. This right here is the key takeaway for safety. Because our bodies contain a lot of water and salt, we are actually really good conductors of electricity. And that means if you touch a live circuit, the electricity will try to use your body as a path, which can cause very serious injury or worse. So please always be careful. So let's do a quick recap. It all starts with a portable power source, the electric cell. That power flows through a circuit, which is just a complete closed loop. A switch gives us control by opening or closing that loop. And the whole system is built from conductors, which let the current flow, and insulators, which keep it all safely on its path. There you have it. You've just unlocked the fundamental principle that powers almost everything around you. And we did it all just by looking inside a simple torchlight. Kind of makes you wonder, doesn't it? What other huge scientific secrets are just hiding in plain sight, waiting for us to take a closer look? Ever thought about what the phone in your hand and the air you breathe have in common? I mean, they seem totally different, right? Well, it turns out they both fall into one of two huge categories that pretty much define everything around us. We're going to dive into that basic split. What makes something a metal versus a non-metal? Okay, so let's kick things off with a little thought experiment. Picture this. You take a hammer to an iron nail. What happens? It flattens out, right? But now, what if you do the same thing to a piece of coal? It just shatters into a million pieces. They're both solid, so what gives? What's the real difference here? And the answer isn't as simple as one being hard and the other being soft. It goes way deeper than that. It's all about a property hidden inside the material, a core characteristic. How something reacts when you apply force, that's one of the biggest tells for figuring out what it's really made of. All right, so let's tackle that first group, metals. We're surrounded by them all the time. Things like iron, copper, aluminum. But what is it exactly that makes us look at something and just know, yep, that's a metal? What are those defining traits? Well, the first clue, and it's a pretty obvious one, is just how they look. You know that shine you get from metals, that special gleam when they catch the light? That's called metallic luster. It's something you just don't see in duller materials like, say, a lump of coal or a chunk of sulfur. And this brings us right back to our hammer and nail mystery. The secret ingredient here is a property called malleability. That's just a fancy word for the ability to be hammered or pressed into thin sheets without, and this is key, without breaking. That's exactly why the iron nail flattens and doesn't shatter. And get this, some metals are just off the charts amazing at this. Take gold and silver. They are the most malleable metals known to us. You can hammer them into sheets so thin they're almost transparent. It's pretty incredible when you think about it. And you see this property in action all over the place. Ever seen that super thin edible silver foil on fancy sweets? Or just the regular old aluminum foil you use to wrap leftovers? That's malleability. It's also the whole principle behind a blacksmith at work, taking a clunky block of iron and hammering it into the shape of a tool, like an axe. So based on all that, you'd think, okay, metals are hard, solid things. And mostly you'd be right. But here's where it gets really interesting, because there are some rule breakers. You've got metals like sodium and potassium that are so soft you could literally cut them with a butter knife. And then there's the ultimate weirdo, mercury. It's the only metal that's a liquid at room temperature. You might have seen it in old school thermometers. Okay, so we've got a good handle on the shiny, bendable world of metals. Now let's flip the script completely and talk about their polar opposites, the nonmetals. Honestly, the simplest way to think about nonmetals is that they're basically the opposite of metals in almost every way. They're usually dull, not shiny. They're brittle, which means they just break or crumble if you hit them. That's why our piece of coal shattered. And they're terrible at conducting heat and electricity. I mean, there's a good reason our electrical wires aren't made of carbon, right? And this group includes a lot of stuff you already know. Carbon, like in coal, is a perfect example. So are things like sulfur and phosphorus. But here's the kicker. Even the oxygen and nitrogen that make up most of the very air we're breathing right now, yep, those are nonmetals too. All right, so we've got these two very different teams, metals and nonmetals, with opposite skills. But so what? Why do we even care about this distinction? Well, it matters a ton, because these very properties are what dictate how we use these materials to build, well, everything. When you look at metals, their properties make them the absolute backbone of our industry and all our technology. Think about it. Their strength and the fact that we can shape them, that gives us tools and buildings. Their rightness and toughness, that's what gets us into space. And their ability to conduct electricity, that powers our entire planet. From a simple iron nail to advanced titanium in a jet, their jobs are tied directly to their properties. But hold on, don't go thinking nonmetals are the B team. They might not be building our skyscrapers or our cars, but they are absolutely critical for something way, way more important: life itself. Just think about how crucial they are for our survival. The nitrogen in the air, we turn that into fertilizers to grow our food. Chlorine, that's what makes our tap water safe to drink. That brownish stuff you put on a cut, that's an iodine solution, another nonmetal working as an antiseptic. So from our farms to our faucets, nonmetals are kind of the unsung heroes of our daily lives. So, we've covered their unique traits and why they're so important. Now, to make sure this all sticks, let's just do a quick side-by-side recap of the biggest differences. Okay, here's the whole story at a glance. You can really see the pattern here, can't you? Whether you're talking about shine or the ability to be shaped, or how well they conduct electricity, even down to their basic chemical reactions, metals and nonmetals are pretty much mirror opposites. It's this stark contrast that makes them such a useful way to categorize the world. Which really leaves us with one last big idea to chew on. We know that metals build our infrastructure, our tools, our tech, and we know that nonmetals are essential for life, for health, for our environment. So the big question is, when you look around at our modern world, how much of it is really just one or the other? Or is most of it actually a clever, carefully designed mix of the two? Kind of makes you see everything a little differently, doesn't it? Our world is in a constant state of motion. I mean, from an ice cube melting in your drink to a mountain slowly turning into dust, everything is changing. But are all those changes the same? Well, it turns out they fall into two big categories: physical and chemical. And understanding the difference between them is, well, it's key to understanding pretty much everything. So let's dive in. Okay, so at first glance, these three things seem totally unrelated, right? But what they share is that they're all examples of the transformations happening all around us, every single day. Let's look at a few more you've definitely seen before. You know how it is? You leave a banana on the counter for a couple of days, and pretty soon it's covered in those brown spots. It even starts to smell sweeter. Something has definitely changed there. Or how about this one? When you're chopping up a cucumber for a salad, you're changing its size and its shape. That's a change too, for sure. And if you look outside, a little bud that was closed up yesterday might have bloomed into a beautiful flower today. See? The world is always in motion. So the big question is, how do we make sense of all these different kinds of changes? Let's start with our first main category: physical change. This one is all about changing how something looks without changing what it actually is. So here's the crucial point. Even though something might look totally different, it's a different shape, a different size, maybe it went from solid to liquid, its fundamental identity, what it's made of, stays exactly the same. No new stuff gets created. Think about these examples. If you fold a piece of paper into an airplane, it's still paper, right? If you inflate a balloon, the rubber just stretches out. And hey, even if you smash a piece of chalk into a fine powder, every single one of those tiny grains is still chalk. You've only changed its form, not what it's made of. And here's a big clue. Think about it. You can unfold the paper, you can let the air out of the balloon. A lot of these changes are reversible. The fact that you can get the original thing back is a giant hint that you're probably looking at a physical change. All right, on to our second category. This is where things get really interesting, truly transformational. We're talking about chemical changes, where you end up with something completely new. And that is the absolute key difference. In a chemical change, the original stuff you started with gets all used up, and it rearranges itself to create something with totally different properties. It's a real transformation. Check out this simple test. If you take a straw and blow bubbles into a glass of plain old tap water, well, you just get bubbles. But if you do the exact same thing with something called lime water, something pretty dramatic happens. The clear liquid starts to turn all milky. So why does it do that? That cloudy look, that's your proof. It's a brand new substance called calcium carbonate that just got made. It wasn't there before. The carbon dioxide from your breath actually reacted with the lime water to create it. You just watched a chemical change happen right before your eyes. And here's the science behind it. On the left, you've got your starting ingredients: calcium hydroxide, which is the lime water, and the carbon dioxide from your breath. Then that little arrow shows the reaction happening. And on the right, you get your brand new substances, the milky calcium carbonate, plus a little bit of water. The original stuff is gone, replaced by something new. Okay, so now that we've got the basic idea down, let's look at some other common and sometimes way more dramatic examples of chemical changes you see all the time. This little setup here shows a pretty classic experiment. It's designed to take the gas that's made in one reaction and see what happens when you bubble it through another liquid. And I bet you've done this one before, mixing vinegar and baking soda. You get that immediate fizzing and all those bubbles, right? Well, that's not just trapped air escaping. That's the creation of a totally new gas, carbon dioxide. Seeing bubbles or fizzing is another huge sign that a chemical change is going on. And there are other dead giveaways to look for. Think about rust. That's a really slow chemical change where iron reacts with oxygen and turns into that new flaky brown stuff called iron oxide. And of course, there's burning or combustion. That's a super fast chemical change that produces new things along with a ton of heat and light. I mean, you can't unburn a log, can you? Okay, now for a real head scratcher. What about something that seems to be doing both types of changes at the exact same time? Let's take a look at a simple candle. So, what do you think? Is the wax just changing its form, or is something totally new being made? Turns out, the answer is, well, it's a little bit of both, and it's fascinating. Let's break this down. First, the solid wax melts into a liquid. That is a classic physical change. If that liquid wax drips down the side and gets hard again, it's still wax. But the flame itself, that's a whole other story. That's the chemical change. The wax vapor is reacting with oxygen in the air to produce entirely new things: light, heat, and gases like carbon dioxide. So yeah, a burning candle is a perfect example of both happening at once. So far, we've been looking at pretty small-scale stuff. But what if I told you that these exact same principles are responsible for shaping our entire planet? It just happens on a much, much, much slower timescale. I mean, the actual ground beneath our feet is a direct product of these two forces working together for millions of years. This whole process is called weathering, and it's how massive, solid rocks get broken down into the soil we need to grow things. So here's how it works. You have physical changes, like water getting into a crack, freezing, expanding, and breaking the rock apart. That's physical weathering. But at the same time, you've got chemical changes happening. Rainwater can be slightly acidic, and over time it reacts with minerals in the rock, dissolving them and changing what the rock is made of. That's how you get soil. And really, that's the big takeaway. On one hand, you have physical changes, which just alter the form of something, and on the other, you have chemical changes, which create something brand new. It's the constant dance between these two that shapes our world. So the next time you see an ice cube melt or a log burning in a fireplace, just remember, you're watching one of the fundamental processes of the universe in action, a universe that is never, ever standing still.
Adolescence. What a word, right? It's probably one of the most transformative and, let's be honest, kind of confusing times in anyone's life. So in this explainer, we're going to try to map out this incredible journey of growth and change, to help make sense of it all.
It often starts with something really simple. A conversation, just like this one, where you suddenly notice things are different. Someone shot up in height, their voice sounds deeper, or maybe there's the first hint of a mustache. These are the little signs, the first markers on that path to growing up.
Okay, so if we're going to navigate this journey, we're going to need a map, right? And any good map starts with knowing what the key terms mean. So let's get right to it. What exactly is adolescence?
The easiest way to think about it is like this. Adolescence is the bridge you cross from childhood to adulthood. It's this super important time.
usually between the ages of 10 and 19, where your body and your mind are basically getting ready for everything that's coming next.
Now, inside that big journey of adolescence, there's a really key process called puberty. So, if adolescence is the whole road trip, think of puberty as the engine of the car. It's the biological powerhouse, the whole physical rewiring that gets the body ready for reproduction. So this physical rewiring, what does that actually look like in the real world? Let's talk about the changes that you can see, the ones that are obvious to us and, well, to everyone else too.
Yeah, one of the first things you might notice is a huge growth spurt. You know that moment when you suddenly realize you're taller than your aunt? You'll also see changes in your body shape, maybe the not-so-welcome appearance of acne, and new hair growing in different places. And for boys, of course, this is when facial hair starts to show up.
Okay, and this next part is super important to remember. Everybody's timeline is different. Seriously, it doesn't matter if these changes happen to you earlier or later than your friends. It is all completely 100% normal. Your journey is yours, and that's it.
You know, there's actually a scientific name for all of these visible changes. They're called secondary sexual characteristics. It's a fancy term, but all it means is these are the signs on the outside that your body is maturing, the things that start to distinguish males from females, even though they aren't the reproductive parts themselves.
And you can see how these paths are pretty different. For boys, you've got the voice getting deeper and the start of a mustache or beard. For girls, some of the big markers are breast development and the start of the menstrual cycle. It's like following two different, but parallel, biological blueprints.
Let's zoom in on one of the biggest internal changes for girls for a second, the menstrual cycle. It's so important to know that this is a totally healthy, totally natural process. It usually happens about once a month, and it's a really clear sign that everything is working just as it should be.
And we have to be super clear about this. There are so many myths out there about menstruation, and honestly, none of them have any scientific basis. Zero. It's just a normal biological function. It's not something to be weird about or scared of.
But hey, the changes aren't just on the outside, right? Not even close. Adolescence brings this huge shift in our emotions too. It can seriously feel like an emotional roller coaster, and figuring out those feelings is just as important as understanding all the physical stuff.
So you might notice you're having these intense mood swings, or you just feel everything more deeply. Well, that's not random. Your brain is literally rewiring itself. The trick is to find ways to channel all that new, powerful emotion in a positive way. Got a lot of energy? Pour it into sports or music. Feeling extra sensitive? That can be fuel for amazing creativity. And that growing feeling of compassion? That can lead you to get involved in making the world a better place.
Okay, so with all this stuff happening, how do you actually handle it all? Let's put together a little toolkit, some real practical advice for navigating this new world.
First thing in the toolkit, hygiene. Yep, it becomes way more important now to keep yourself clean and prevent infections. We're talking daily washing, paying attention to areas like armpits, and for girls, good hygiene during menstruation is absolutely key for staying comfortable and healthy.
And of course, in today's world, a huge part of being a teen is being online, and that can bring its own challenges, like cyberbullying. If that ever happens, the most important thing is don't be scared and don't feel helpless. You have a defense plan. Step 1, tell a parent or a teacher right away. Step 2, be really careful about what pictures you post. And Step 3, never, ever share your personal info with strangers.
Look, being curious is a totally normal part of being a teenager, but it's so important to be aware of the real dangers out there. Things like tobacco, alcohol, and drugs, they're not just bad for you, they're addictive. And that means just one time can easily and very quickly turn into a huge problem.
So what do you do? What's the plan? It's actually really simple, but it's powerful. You just say no. The first time and every time after that. You have to understand that the risk of addiction starts with that very first time. And please remember this. If you or a friend needs help, you are not alone. There's always support from family, friends, and trusted adults, and even professional helplines like this one.
You know, this whole journey doesn't have to be scary or overwhelming. Not at all. By building a solid foundation of healthy habits, you can actually make your teenage years a really positive and even joyful time.
Think about it. Your body is doing a ton of work right now. It's growing and changing like crazy. So it needs the right fuel. And we can get really specific here. The calcium you get from milk or cheese, that's not just good for you, it's literally for building stronger bones. The iron you get from spinach or beans, that's essential for making blood.
You are, quite literally, building your future adult body with every single meal.
So if you boil it all down, what's the secret to a healthy journey through adolescence? It really rests on 4 main pillars: eating good food, keeping up with hygiene, getting regular exercise, and maybe the most important one of all, making thoughtful, responsible decisions for yourself.
So, we've talked about all the whats of these changes. But what about the why? What's the secret engine driving all of this? Well, the answer is hormones. Think of them like tiny chemical messengers inside your body, acting like the conductor of a huge orchestra, coordinating everything from your growth spurts to your mood swings.
So, in the end, adolescence is a journey that everyone goes on. But your path, that's completely your own. By understanding what's happening, knowing when to ask for help, and making good choices, you're the one in the driver's seat. The map is right there in your hands. So the real question is, how will you choose to navigate your journey?
Heat. It's literally all around us. It cooks our food, it warms our homes, and believe it or not, it drives the weather for the entire planet. But how does it actually move? Well, it turns out heat travels in some incredibly clever ways, often right under our noses. So let's follow the journey of heat, starting with something simple and ending with, well, the whole world.
It all kicks off with a simple question. Let's say you're cooking. You put a metal pan on the stove, and pretty soon the whole thing is scorching hot. But the handle, which is often made of plastic or wood, stays cool enough to touch. So what's the deal with that? Why the difference? Well, the answer to that pan mystery lies in our first method of heat transfer, conduction. And it's exactly what it sounds like, heat that travels through direct touch. To really see this in action, picture a simple but kind of brilliant experiment. We take a metal strip and we stick a few pins to it with wax, all in a nice, neat row. Then we take a candle and heat up just one end of the strip. What do you think is going to happen? Yup, exactly what you'd guess. The pin closest to the flame drops first because its wax melts. But then, like a slow-motion domino effect, the next pin falls and then the one after that. It's a perfect visual of heat literally marching its way down the solid metal strip. So, here's the key takeaway. Conduction is how heat moves through solids. The tiny particles in the metal get energized and start vibrating like crazy, bumping into their neighbors and passing that energy along. The particles themselves don't go anywhere. They just pass the heat down the line. Metals are fantastic at this, which is why your pan gets hot all over. Okay, so that covers solids. But what about stuff that flows, like liquids and gases? They play by a different set of rules. Their secret is our second method of heat transfer, convection. Think about it for a second. When you see a campfire or smoke coming out of a chimney, it doesn't just spread out in every direction, right? It always rises upwards. And that's not a coincidence. It's actually a massive clue about how heat moves through fluids. And this is the big difference, so you gotta get this. In conduction, the particles stay put. But in convection, the hot particles themselves physically move from one place to another, carrying all that heat energy with them. When you heat up air, it expands, gets less dense, and, you guessed it, it rises. That's why smoke goes up. And this isn't just about small things like campfires. Convection happens on a massive scale. Picture this, you're at the beach on a hot day. The land heats up way faster than the water, so the hot air over the sand rises, and what happens? The cooler, heavier air from over the sea rushes in to take its place. That's your sea breeze. And at night, the whole thing flips. That's a giant convection current right there. So we have conduction for solids, convection for fluids, but there's still a huge piece of the puzzle missing. Think about the sun. The space between us and the sun is a basically empty vacuum. There's no solid to touch, no air to move. So how on earth does the sun's heat get to us? Well, that brings us to our third and final method, radiation. You absolutely know this feeling. You're sitting near a fire, you're not touching it, so it can't be conduction, and you might be sitting off to the side, not in the path of the rising hot air, so it's not just convection. And yet you can feel that amazing warmth on your face. How? And that is radiation. Heat can travel as invisible energy waves, kind of like light waves. And the craziest part? It doesn't need any medium to travel through. No solids, no liquids, no gases. It can just beam across the vast, empty vacuum of space. It's how our sun warms the entire planet from 93 million miles away.
And this explains something you probably do all the time without even thinking about it. Why do we wear light-colored clothes in the summer? Because those light surfaces reflect most of the sun's radiation, which helps keep us cool. And in the winter, dark clothes are your friend because they absorb more of that radiation, helping you stay warm. It's just basic physics in your closet. Okay, now let's put it all together. Check out this brilliant device from the Himalayas, the Bukhari heater. It uses all three methods of heat transfer at the same time. The metal top gets hot through conduction, making it perfect for cooking. It heats the air around it, which then circulates through the room by convection, and at the same time, it radiates heat waves, warming up anyone sitting nearby. It's a perfect little masterpiece of heat engineering. So we've seen how heat works in a cooking pan, a sea breeze, and a room heater. Now, let's zoom all the way out and see how these exact same principles power one of the most important systems on our entire planet, the water cycle. When you get right down to it, the water cycle is just a giant solar-powered engine that moves water all around the globe. It's this continuous loop of evaporation, condensation, precipitation, and collection. And you know what the fuel for this whole engine is? Heat. So how does it all kick off? Well, it starts with the sun's energy traveling through the vacuum of space via radiation. That energy hits our oceans, lakes, and rivers, and it heats the water up enough to turn it from a liquid into a gas. We call that water vapor, and it immediately starts to rise. And as that warm, moist air rises, what's driving it upward? That's right, convection. These huge air currents carry the water vapor high up into the atmosphere, where things get a lot colder. That chill causes the vapor to cool down and condense back into tiny little droplets of liquid water, forming the clouds we see. Eventually, all those tiny droplets start bumping into each other and clumping together. The clouds get heavier and heavier until they just can't hold all that water anymore. So the cycle releases it back to the Earth's surface as precipitation, which could be rain, snow, or hail, all depending on the temperature up there. And once that water hits the ground, it starts to collect. Some of it flows over the land into rivers and lakes, making its way back to the ocean. But a lot of it also seeps deep into the ground through a process we call infiltration, storing huge amounts of fresh water right beneath our feet. And where does that seeped-in water go? It's stored in these amazing natural underground reservoirs called aquifers. They're basically huge layers of porous rock and sand that hold on to fresh water. This groundwater is a critical part of the water cycle, and it's where we get a lot of our drinking water. So there you have it. From the way a simple pan heats up to the massive engine that powers our planet's water system, it all comes down to conduction, convection, and radiation. The water cycle is nature's perfect recycling program. But that brings us to a really important final thought. We rely so much on that groundwater stored in aquifers. With groundwater levels falling around the world, it makes you wonder, are we drawing from that account faster than nature can make deposits? Have you ever watched a race and wondered how we can measure it down to 1,000th of a second? It's pretty amazing, and something we kind of take for granted. Today, we're going to dive into the incredible journey of how humanity figured out how to measure two of the most fundamental things in our universe, time and motion. So this whole explainer kicks off with a really great question from a girl named Prerna. She's watching this super tight sprint, a real photo finish, and she starts to wonder, before we had all these fancy stopwatches and digital timers, how did anyone even know what time it was? To get to the bottom of Prerna's question, we need to go way, way back to a time before the first clocks were even invented. And you might be surprised to learn that humanity's first clock wasn't a machine at all. It was the world itself. You see, long before we had gears or batteries, our ancestors just looked up. They saw that the sun always rose and set, giving them the day. They watched the moon cycle through its phases, which gave them the month. And of course, they felt the seasons change in a predictable rhythm, giving them the year. Nature was the original giant clock for all of humanity. Okay, but a whole day is a pretty big chunk of time, right? People needed a way to measure smaller bits, like hours. So they got really creative and started building some truly ingenious devices to keep track of the day as it passed. First up, the sundial. This one's a classic for sure. You just stick something in the ground and watch its shadow move as the sun travels across the sky. It was simple, it was elegant, and for the first time, it let people organize their day around a shared schedule. As long as the sun was out, of course. So what happens when it gets dark or on a cloudy day? The sundial's not much help then, is it? Well, that's where the water clock comes in. By letting water drip at a perfectly steady rate from one pot to another, you could measure time's passage, day or night. This was a huge leap forward. And, it's that same basic idea of a steady flow that gives us the hourglass. But instead of water, it uses fine sand. The best part, it's portable, it's reliable, and it has absolutely nothing to do with the sun. So these early clocks were seriously clever, but the quest for even more precision was really just getting started. And the next giant leap forward didn't come from a fancy workshop. Nope, it came from a simple observation in a church.
The story goes like this. The famous scientist Galileo Galilei is sitting in church, maybe a little bit bored, and he notices a lamp swinging back and forth. Now, the only timer he had on him was his own pulse. So he starts counting, and he discovers something amazing. Every single swing of that lamp, whether it was a big arc or a small one, took the exact same amount of time.
And this observation led to a concept that is absolutely fundamental in physics, the time period. That's just the scientific term for the time it takes a pendulum to make one complete swing. What Galileo figured out was that for a pendulum of a certain length, that time period never changes. All of a sudden, we had a way to measure time that was constant, predictable, and super reliable.
So let's break that down. What's one full swing, or what scientists call an oscillation? Well, imagine the pendulum bob hanging still at the center. That's position O. It swings out to one side, A, then all the way across to the other side, B, and then right back to the center, O. That whole journey is one oscillation.
A discovery like this just opens up a whole new world of questions, right? So let's think like Galileo for a second. Would a really, really long pendulum have the same time period as a short one? How would you even set up an experiment to test that? It's this kind of curiosity that really drives science forward. Okay, so once we had a truly reliable way to measure time, thanks to Galileo's pendulum, something else became possible. For the first time, we could start to accurately measure motion.
And that brings us directly to a concept we all use pretty much every single day: speed. It's a really powerful idea, but it's also incredibly simple. It's as simple as this. You take the distance something traveled and you divide it by the time it took to get there. That's it. That's speed.
And you see this in action every time you're in a car. The speedometer is telling you your speed right now, in real time. And the odometer? That's tracking the total distance you've traveled. It's the perfect everyday example of measuring time and motion working together.
All right, so now that we can calculate speed, we can get even more specific. We can actually start to describe how something is moving. Is it cruising along at a steady pace, or is it speeding up and slowing down? And that basically boils down to two key types of motion. On one hand, you have uniform motion. The best way to think about this is a car with cruise control set on a long, straight, empty highway. It covers the exact same distance in every equal interval of time. On the other hand, you have non-uniform motion. Now imagine that same car in city traffic. It's speeding up, slowing down, stopping. It's covering unequal distances in equal intervals of time. Okay, let's look at some actual numbers. This table makes the difference super clear. Check out train X. In the first 10 minutes, it goes 20 kilometers. In the next 10 minutes, another 20 kilometers. It's perfectly consistent. That's uniform motion. But now look at train Y. It starts off the same 20 kilometers in 10 minutes, but in the next 10 minutes, it only covers 16 kilometers. Its speed is changing. That's non-uniform motion right there. So let's do a quick recap of this whole journey. We started with our earliest ancestors just looking at the sun and moon. Then they invented some brilliant devices like sundials and water clocks. After that, Galileo's incredible observation about the pendulum completely changed the game. That breakthrough allowed us to finally define and calculate speed, which in turn lets us understand the crucial difference between uniform and non-uniform motion. And that leaves us with one final thought to chew on. Galileo used the only tool he had on hand, his own heartbeat, to make a revolutionary scientific discovery. So my question to you is this: if every clock in the world suddenly stopped, what repeating cycle in your own life, your body, or the world around you could you use to start telling time again? Have you ever really stopped to think about how that apple you just ate becomes the energy you need to walk, to think, or even just to breathe? Well, in this explainer, we're going to follow that incredible journey, right from food to fuel. So let's start with a bit of a puzzle.
We all know we eat for energy, right? But the food itself, an apple, a piece of bread, you name it, is pretty much useless to our cells in the form we eat it. So how on earth do we get from a bite of food to the power we need for every single thing we do? To solve that puzzle, our body has this amazing process that's kind of like a factory assembly line mixed with a high-tech chemical lab. It's a whole system designed to take our food apart piece by piece and unlock all that power that's hidden inside. And that process has a name you already know: digestion. It's the first and absolutely essential step on this internal journey. It takes those big, complex things in our food and breaks them down into simple little bits that our body can actually put to work. Now, this whole breakdown doesn't just happen randomly all over the place. Nope. It all happens along one single long continuous tube. You can think of it like a winding road our food has to travel down, a path that's known as the alimentary canal. So this path, this road, it starts in the mouth, goes down the esophagus, churns around in the stomach, and then winds its way through the small and large intestines. And at every single stop along the way, the food gets transformed until finally whatever the body can't use gets sent out the other end. And the breakdown begins literally the second that food enters your mouth. There are two things happening at once. First, your teeth are doing the mechanical work, crushing and grinding. But at the exact same time, your saliva starts the chemical work, using special enzymes to go after those complex carbs. You can actually experience this chemical digestion for yourself. Seriously, try it. If you take a piece of plain rice or bread and just chew it for a minute or so, you'll start to notice it tastes sweet. That's it. That's your saliva breaking down the starch into simple sugars, right there in your mouth. Pretty cool, huh? Okay, so after the mouth, food heads down the esophagus to the next major stop, the stomach. And believe it or not, our first real understanding of what happens in there didn't come from some planned experiment. It came from a completely bizarre and fascinating accident. Get this. Back in 1822, a guy named Alexis St. Martin survived a shotgun blast that left him with a permanent hole straight into his stomach. For his doctor, William Beaumont, this was a literal window into a hidden world. He could actually watch digestion happening in real time and made some incredible discoveries because of it. Now, after the stomach, the partially digested food moves into the longest and maybe the most important part of its whole journey, the small intestine. And its length is, well, it's truly staggering. 6 meters. That's about 20 feet, all coiled up inside you. To put that in perspective, that's nearly twice the height of a typical classroom. So why so long? Well, that massive length is all about maximizing the time and the surface area for one absolutely critical job: absorbing nutrients. And that brings us to the main event of this whole digestive journey. Everything up to this point has been about breaking things down. Now, in the small intestine, we get the real payoff. It's time to absorb all the good stuff. So in here, a final cocktail of digestive juices gets to work. You've got bile from the liver that takes care of the fats, and you've got powerful enzymes from the pancreas to finish off the proteins and carbs. Once everything is broken down into its simplest little molecules, the walls of the intestines soak up all those valuable nutrients and send them into your bloodstream to be delivered all over your body. So what about the leftovers? Well, anything that couldn't be absorbed moves on to the large intestine. It's much shorter, only about 1.5 meters, but it's wider. And its main job isn't really absorbing nutrients anymore. It's all about recycling water from that undigested food back into the body. But look, just absorbing the nutrients is only half the story. Now we've got the fuel, but we still need to turn that fuel into fire, into energy we can actually use. And for that, we need a key ingredient that we get from the air. Okay, so here's where we need to be super clear about something. We tend to use the words breathing and respiration like they're the same thing, but they are not. Breathing is just the physical part, moving air in and out of your lungs. Respiration, that's the chemical process that happens inside every single one of your cells. It's the part that actually uses the oxygen to get the energy out of your food. This simple little equation right here, this is the reaction that powers your entire life. It's called cellular respiration. It takes glucose, that's the fuel from your food, and combines it with the oxygen you breathe. This reaction burns the glucose, which releases a burst of energy for your cells, leaving just carbon dioxide and water behind. Of course, humans aren't the only ones with these amazing systems.
But when you look across the animal kingdom, you see they can look very, very different. We see all these incredible adaptations for different diets and different environments. For example, just compare our digestive system to a cow's. Animals that eat tough grass, called ruminants, have these wild, complex stomachs with multiple chambers, all to break down plant stuff that we could never, ever digest. And the adaptations for breathing are just as diverse. I mean, we use lungs to grab oxygen from the air, but fish have evolved these intricate gills that let them pull dissolved oxygen straight out of the water they live in. It's a completely different solution to the same problem. And the variety is just astounding. Birds have extra air sacs to make their breathing super efficient for flying. Frogs can use lungs, but they can also absorb oxygen right through their skin when they're in the water. And then you have earthworms, which breathe entirely through their skin. Each one is a perfect solution, evolved for a very specific way of life. So, the next time you take a bite of food, or just a simple breath, take a second to remember that complex, automatic world you're setting into motion. It's an incredible journey that's constantly turning the simplest things we do into the very energy that, well, makes us who we are.
You know, there's this incredible secret process happening all around us, in every park, every forest, even in your own backyard. It's something that powers almost all life on Earth. Plants are making their own food, basically out of thin air. So let's figure out just how they pull it off.
Now really, just stop and think about that for a second. How does a tiny little seed, with just a bit of soil and water, grow into a gigantic tree that weighs thousands of pounds? I mean, it doesn't go hunting, it doesn't graze. So where does all that mass actually come from?
We see animals eating all the time, right? It's obvious. But plants? We watch them grow and flower, and we see them change with the seasons, but we never ever see them sit down for a meal. It's a real mystery. How are they fueling all this amazing growth?
All right, to crack this case, we've got to start thinking like detectives. Let's look for the most basic clues. What are the absolute essentials that plants need to survive? A simple experiment should give us our first lead.
Okay, here's the setup. We've got 3 identical plants. Plant A, it gets the good life. Lots of sun, plenty of water. Plant B gets all the sun it wants, but we're not going to give it any water. And plant C, it gets water, but we're going to stick it in a dark closet. No sunlight. So what do you think is going to happen?
And the results are in. No surprise, plant A is thriving and poor plant B totally withered without any water. But check out plant C. Even with all the water it needed, the lack of sunlight meant it barely grew, and its leaves started turning yellow. It was just hanging on. And that right there gives us our first huge clue. For a plant to really grow and be healthy, it's not enough to have just sunlight or just water. It needs both. If you take one of those away, the whole system just kind of falls apart.
Okay, so we know what they need, but where does all the magic actually happen? For that, we need to zoom in and take a look at the plant's main headquarters.
Turns out, the leaf is where all the action is. You could think of every single leaf as a tiny solar-powered food factory. This is the spot where the plant makes and stores its energy, mostly in the form of starch, which is just a complex sugar.
So, why are these little factories green? Well, that's because of a special pigment called chlorophyll. And this stuff is absolutely crucial. It's the key piece of machinery in the whole factory. Its job is to capture the energy from sunlight, acting like a tiny, super-efficient solar panel.
But hey, how can we be so sure that food is actually being made there? Well, scientists have this really neat trick. If you use a simple iodine solution, you can test a leaf for starch. And if that leaf has been busy making food, the iodine turns it this deep blue-black color. It's visible proof that the factory is up and running.
So we've got sunlight for energy and water coming up from the ground. But there is one more critical ingredient, and this is the most surprising one of all. It actually comes from the very air we're breathing right now.
Check out this clever little experiment. You take one leaf on a living plant and you seal part of it inside a bottle. Now, this bottle has a chemical in it that sucks up all the carbon dioxide. The other half of the leaf is just left outside in the regular air. Then, you put the whole thing in the sun for a while.
After a few hours, we do that iodine test on the whole leaf, and the result is amazing. The part of the leaf that was outside in the air, with access to CO2, turns blue-black. It was making starch.
But the half that was inside the bottle, completely starved of CO2, shows no starch at all. The food factory was shut down.
And there it is. That's our second huge clue. Confirmed. Plants are literally building themselves by pulling one of their main ingredients right out of thin air. That ingredient is carbon dioxide.
Okay, we've gathered all the evidence, we know the location, we've got the energy source, and we've identified all the raw materials. It is time to put all the pieces together and finally name this incredible process.
So, let's just run through our checklist of clues one more time. We have sunlight, which is the power source. We have water, which gets pulled up from the soil through the roots. We have carbon dioxide, taken straight from the air. And we have the chlorophyll in the leaves, the special stuff that makes it all happen.
This whole amazing solution to our mystery has a name: photosynthesis. It's pretty simple when you break it down. Photo means light, and synthesis means to make something. So plants are literally using light to make their own food from water and carbon dioxide. And oh yeah, as a little byproduct, they release oxygen, which is kind of important for us.
So here it is, the secret recipe that basically runs our entire planet. The plant takes in carbon dioxide and water. It uses sunlight like an oven to cook it all up, and what comes out is glucose. That's a simple sugar for energy, and the oxygen we all breathe.
But hold on, making the food is only half the story. I mean, how does the water get all the way from the roots up to the leaves? And then how does that sugary food get sent back out to the rest of the plant? Well, it turns out plants have their own amazing internal highway system.
So inside every plant is this incredible plumbing. There's one network of tubes called the xylem. Think of it as a one-way street constantly pulling water and minerals up from the roots to the leaf factories. Then there's a second network, the phloem, that carries the sugary food down from the leaves to every other part of the plant that needs energy.
And how do we know this for sure? Well, you can see it yourself with a super simple proof. If you take something like a celery stalk and just stick it in some water with red food coloring, the plant will just drink it up. And within a day or so, you'll start to see these fine red lines traveling all the way up the stem and into the leaves.
What are those red lines? That's the xylem. That's the one-way highway system in action, pulling that colored water all the way up. It's the perfect visual, showing exactly how water gets delivered to those food factories in the leaves.
So the main takeaway here is just astounding. Plants are basically master chemists. They take three simple non-living things, sunlight, water, and air, and they transform them into food for themselves and the very oxygen that makes all of our lives possible.
Every single leaf you see is a tiny factory, quietly performing a miracle that keeps our planet running. They are literally building our world and our atmosphere, breath by breath, just by making their lunch. Kind of makes you look at a simple blade of grass a little differently, doesn't it?
Have you ever just stopped and looked at the way sunlight streams through a window? Or the way the moon glows at night? Light is everywhere, and it literally paints our world. But behind all that beauty, there's a fascinating science. A set of really simple rules that explain every single shadow and reflection we see. So let's dive in and explore those rules together. Okay, I want you to imagine something. You're in a village, way out in the countryside, far from any city lights. The night isn't totally dark, though. Nope. Instead, it is absolutely alive with this magical dance of hundreds of fireflies, flashing their lights on and off. It's incredible. Well, this is a sight a young boy named Keshav actually saw, and it's what started his whole journey of curiosity into what light really is. I mean, you've got the moon, the stars, those fireflies, maybe the headlights of a bus passing by. It really makes you wonder, right? Do all these things create their own light, or are some of them just borrowing it? That's the very first question we're going to tackle. To figure this out, first things first, we've got to get organized. You know, scientists love to put things into categories, and when it comes to light, pretty much everything in the entire universe falls into one of two super simple groups. So on one side, we have what we call luminous objects. These are the light makers. Think of the sun, those fireflies we were just talking about, or even a simple flashlight. They're all generating their own light. Then on the other side, we have non-luminous objects. These guys don't make any light at all, they just bounce it back. That could be the moon or, the chair you're sitting on right now.
And just like that, this simple difference answers one of our biggest questions right off the bat. The moon, even with its beautiful bright glow, is not a light source. It's really just a giant reflector, bouncing sunlight all the way back to us here on Earth. So, in a way, moonlight is really just sunlight in disguise. Kinda cool, right?
Okay, so now we know where light comes from. But what about how it travels? How does it get from point A to point B? Does it weave and curve all over the place, or does it follow a much stricter rule? Well, it turns out light is actually pretty predictable. And we can prove this with a brilliantly simple experiment. Imagine taking 3 matchboxes, poking a hole in the exact same spot on each one, and then lining them up perfectly straight. When you shine a flashlight through that first hole, what do you see? A bright spot of light appears on a screen at the very end. The path is totally clear.
But here's the fun part. What happens if you just nudge one of those matchboxes, just a little bit, out of line? Poof, the spot of light is gone, vanished. The path is broken. Now this tells us something really important. The light couldn't just bend or curve around that misaligned hole to get to the screen.
If you're still not convinced, try picturing this one. Look at a candle flame through a straight, hollow pipe. No problem, right? You can see it perfectly. Now, what if you bend that pipe? Can you still see the flame? Nope, it's completely gone from your view. The takeaway from both of these little experiments is simple, but it is so powerful. Light travels in straight lines. This one single principle is the absolute key to understanding everything that comes next, from how shadows are made to how reflections work. So now that we know for sure that light travels in a straight line, a brand new question pops up. What happens when something gets in its way? Well, it really depends on the material that's doing the blocking. You've got transparent things, like glass, which let light pass right on through. Then there are translucent materials, like tracing paper, that let some light through but kind of scatter it all over the place. And finally, you have opaque objects, like a piece of cardboard, that block light completely. And it's these opaque objects that are the real stars of our next topic. You know, creating a shadow is kind of like following a simple 3-step recipe. First, you need a source of light, say a flashlight. Second, you need an opaque object to block that light. And third, you need a screen, like a wall, for the shadow to actually show up on. And that's all a shadow really is. It isn't a thing by itself, but actually the absence of something. It's just that dark patch that gets created because the straight path of light was interrupted by an object it couldn't travel through. So we know opaque objects block light. But what if that object is also super shiny, like a mirror? Well, it doesn't just block the light. It actually sends it careening off in a whole new direction. It makes light bounce. And this bouncing has a fancy scientific name, reflection. It's simply the process of light hitting a shiny surface and changing its direction, heading off on a brand new but still straight path. You can see this happen so clearly with another great little experiment. If you create a single thin beam of light, you can do this with a flashlight and a comb. You can see its perfectly straight path on a piece of paper. Now stick a mirror in its way. Instantly, that beam hits the mirror and angles off in a completely new direction. That is reflection in action, right there. Now, this bouncing of light is how we see pretty much everything. But in a mirror, it does something even more incredible. It creates an image, a perfect copy of the world that's right in front of it. The images you see in a flat or plain mirror always follow some very specific rules. They are always the exact same size as the real object, and they're always upright, not upside down. But here's where it gets really interesting. In a mirror, left and right are swapped. The scientific term for this little switcheroo is lateral inversion. And this is the perfect example. I bet you've noticed that the word ambulance is written backwards on the front of the vehicle. That's not a mistake. It's designed that way on purpose, so that when a driver up ahead looks in their rearview mirror, that lateral inversion flips it back the right way, making it instantly readable. It's literally a life-saving use of physics. How cool is that? All right, let's do a quick recap of our journey. We figured out that objects either make light or they just reflect it. We proved that light travels in straight lines, which, as it turns out, is the exact reason shadows are formed when that path gets blocked. And finally, we saw how shiny surfaces don't just block light, they reflect it, creating those fascinating, and sometimes backwards, mirror image worlds. So I'm going to leave you with one final little puzzle to think about. Using everything we just learned, Why do you think we can see the shadow of a bird when it's flying low to the ground, but that very same shadow seems to just disappear when the bird flies way up high in the sky? The answer is hidden in the journey we just took. Keep looking and definitely keep asking why. You know when you look up and watch the sun travel across the sky, from sunrise all the way to sunset? It seems so obvious, right? The sun is the one doing all the moving. But what if I told you that what you see, what you feel, it's all part of a grand illusion? So let's dive in and unravel this incredible cosmic puzzle together. So, here's the big question, the one that changes everything. Does the sun actually move across our sky, or do we? Our entire perception of day and night, it all hangs on the answer to this one question. You know, this whole puzzle really starts with something super simple, a shadow. A student named Rashmika noticed that her shadow was really long in the morning, but then super short in the afternoon. So she thought, okay, the sun must be moving. But then she remembered being taught that the Earth moves around the sun. It's a total paradox, right? So which one is it? To crack this cosmic code, we don't need a rocket ship. Nope. We just need a trip to the local playground. That's right, a merry-go-round. This simple ride, believe it or not, holds the key to understanding a huge concept called relative motion. Okay, so picture this. You're on a merry-go-round and it's spinning anti-clockwise. Now look out at the world. What do you see? The trees, the benches, the whole park, it all looks like it's moving past you in the opposite direction, clockwise. But you know, deep down, the park isn't going anywhere. It's you. You're the one who's moving. And that right there leads to the big what if. What if the Earth is just our giant cosmic merry-go-round, and the sun is just like one of those stationary trees in the park? Let's take a look at the first of Earth's two really important movements. This brings us to the first piece of the puzzle, Earth's daily spin, or what we call rotation. So what is rotation? Well, just think of the Earth as a spinning top. It's constantly turning on this imaginary line that goes right through it, and that line is called its axis. One complete turn takes about 24 hours, which, of course, is what gives us our day. And you can actually see how this works with a super simple experiment. Just take a globe and shine a flashlight on it. The part of the globe the light hits, that's daytime. The other half, in the dark, that's nighttime. Now, as the globe spins, different parts are constantly moving into the light and then back out again. That's day and night. And this is the big reveal. This is the answer to our merry-go-round puzzle. See, the Earth spins from west to east. So just like the trees in the park seem to move in the opposite direction, the sun appears to us to be moving in the opposite direction, from east to west. Let's just walk through your day. In the morning, the spot you're on Earth rotates into the sunlight. From your perspective, the sun appears in the east. By noon, you're facing it head-on. Then, in the evening, you keep rotating away from it so it looks like it's disappearing in the west. The sun never moved. You did. And you know what? This idea is not new. Not by a long shot. Way back in the 5th century, the incredible Indian astronomer Aryabhata figured this out. He said it was just like being on a moving boat and watching the shoreline seem to slide backwards. He knew it was our own motion that created the illusion. Amazing, right? And the proof? It's literally all around us every night. If you look up, the pole star, Polaris, seems to stay perfectly still because it's almost directly above our North Pole. As we spin, all the other stars appear to circle around it. That's what creates those beautiful arcing star trail photos. And it's not just the sun and stars. The moon does the exact same thing, rising in the east and setting in the west, for the very same reason. But just spinning in place is only half the story. The Earth is also on a much, much longer journey. Okay, so this second major movement is called revolution. While the Earth is spinning on its axis every 24 hours, it's also moving in a gigantic loop, or orbit, around the sun. And that whole trip takes about 365 days to complete, which gives us our year. So let's put these side by side just to make it super clear. Rotation, that's the 24-hour spin that causes day and night. Revolution, that's the 365-day orbit that changes the stars we see and gives us our seasons. Two totally different motions, and they're both happening all the time. You know how you see different constellations in the winter than you do in the summer? Ever wondered why?
Well, that's revolution in action. As we orbit the sun, the nighttime side of our planet is always facing a different direction in deep space, revealing a whole new backdrop of distant stars as the year goes on. And here's one last crucial piece of the puzzle. The Earth's axis isn't perfectly straight up and down. It's actually tilted. And it's that tilt, combined with our year-long journey around the sun, that gives us seasons. It's not about being closer or farther from the sun, but all about which half of the planet is tilted toward it. Okay, let's bring it all together and step back onto our cosmic merry-go-round one last time. So the solution to that puzzle we started with, Rashmika's puzzle, it's crystal clear now. The sun isn't the one racing across our sky every day. We are. We're standing on the surface of a planet that is spinning like a top and hurtling through space in a giant orbit, all at the same time. So the next time you watch a sunrise or a sunset, just take a second and remember what's really happening. You're not actually watching the sun move at all. You are feeling the turn of the Earth. Our sense of just standing still, that might be the most profound and the most beautiful illusion of them all.